So this question or this problem's worded a little bit tricky, but we will read through it. So a crystalline solid consists of atoms stacked up in a repeating lattice structure. Consider a crystal as shown below. The atoms reside at the corners of the cubes of side L equals 0.200 nanometers. So what they mean by this is that the circles are actually the cubes or the spheres, like so. And they said the atoms reside at the corners, so like this. Where I'm drawing the circles, that's where the atoms are. And they also say, so the atoms reside at the corners of cubes of side L equals 0.200 nanometers. So this means this is 0.200 nanometers. This is L, 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 so forth. L, so forth. These are all side L. Oops. 0.200 nanometers. One piece of evidence for the regular arrangement of atoms comes from the flat surface along which a crystal separates or cleaves when it's broken. Suppose this crystal cleaves along a face diagonal as shown in the bottom picture. Calculate the spacing d between two adjacent atomic planes that separate when the crystal cleaves. So there's more than one set of planes. For example, you can see this is a plane right here, the top one. And here is another set of plane, another plane. And here's another one, and so forth. And then when the crystal was cut, it was cut along this diagonal plane right here. You can see it. Diagonal plane right here. And here's the second one behind it. There's another plane, and so forth. So, calculate the spacing d between two adjacent atomic planes that separate when the crystalline cleaves. So when it was cut, it wants us to find the distance between these planes, these diagonal ones, this distance here, this distance, whatever this distance is between the diagonal planes. So we should be able to figure that out. So where I'm drawing the green line, that's where the diagonal planes are. So this would be one, this would be a diagonal plane, this would be a diagonal plane. And we know from earlier, the atoms reside, this sentence right here, the atoms reside at the corners of cubes of side L equals 200 nanometers. So L equals 200 nanometers. So we know the distance between the planes on the bottom is L, or 200 nanometers. And we know the distance between this atom and this atom is also 200 nanometers. So this is L, this is L. And we need to find this distance between the planes. So what we should start out with is taking this triangle here and figuring out the hypotenuse first. So we can bring that out here and blow this up. And the green will be the hypotenuse. And these sides are side L. So to figure out the hypotenuse, we can use, this is a right triangle, so we can use Pythagorean's theorem, which says a squared plus b squared equals c squared. In our case, it's going to be L squared plus L squared equals H squared. So we write L squared plus L squared equals H squared. We can say this, rewrite this as 2L squared equals H squared. Take the square root of both sides, we will get L times the square root of 2 equals H. So H equals L times the square root of 2. And remember, we want to find the distance between the two planes. So this is one plane, and if you imagine the rest of the atoms in the lattice, this would be the second plane. So we want to find the distance. We want to find the distance between these. And so a way to do that we would recognize that this is another triangle, and we know what this length is, right? This length right here, it's just half of this. So we can rewrite that as this is L times the square root of 2 divided by 2. And since this whole thing, this is half of a square, we know that this length and this length are going to be the same. So we found our distance between the two planes. So we can say d equals L times the square root of 2 over 2, which equals, and I will get our calculator out. Come on. So, alright, our L is equal to 0.200 nanometers. So 0.200 times the square root of 2 divided by 2 is 0.141421, etc. So 0.14142 dot dot dot. And we want to take note of the information that we were originally given contains 3 significant digits. So we need to make sure we answer in the same way. So our final answer would be D equals 0.141, and this I will not round the 1 up because the number after it is less than 5. So our final answer, 0.141 nanometers, and we're done.